You learned the solar system as a finished thing. 8 planets, a couple of belts of rubble, and then the long dark. It feels complete, the way a familiar room feels complete even with the lights off. But out past Neptune, a handful of icy worlds swing around the sun on orbits that all lean the same way, tilted and pointed in nearly the same direction, as if a hand you cannot see had combed them into line. That pattern is the reason some astronomers believe in Planet 9, a 9th planet hiding far beyond Pluto, cold and slow and unlit. Tonight we follow that idea all the way out. The strange part is that the best clue we have ever found, a faint dot buried in 2 infrared surveys taken 23 years apart, may not be the planet anyone predicted. And if it is real, it could mean the original picture was wrong. So we start at the edge and work outward. Picture the solar system laid out flat the way it hangs in a classroom. The sun sits in the middle, warm and heavy. Close in, 4 small rocky worlds circle fast: Mercury, Venus, Earth, and Mars. Farther out, 4 giants move slowly: Jupiter, Saturn, Uranus, and Neptune. That is the tidy version, the one most of us carry from childhood. It ends at Neptune, and past Neptune there seems to be nothing but cold and distance. The real edge is stranger and much larger. Just beyond Neptune lies the Kuiper Belt, a wide ring of icy leftovers from the birth of the planets. Pluto lives there, and so do thousands of smaller frozen worlds. To measure these distances, astronomers use a simple ruler called the astronomical unit. 1 astronomical unit is the distance from the Earth to the Sun. Neptune orbits at about 30 of them. The Kuiper Belt thins out around 50, and then, for a long stretch, the map really does go quiet. But quiet is not the same as empty. Sunlight out there is a thin grey thing. A person standing on a Kuiper Belt object would see the sun as a brilliant point, too small to be a disk, casting shadows as sharp as a moonlit night on Earth. Everything is slow. A single lap around the sun can take hundreds of years. Nothing hurries at the edge of the map. If this is your kind of quiet, the slow and patient corner of the universe, this channel is built for exactly that, and following along is the easiest way to keep these long journeys coming. For most of history, we assumed the map was finished. 8 planets, a belt of ice, and the dark. The planets had been counted, named, and measured. There was no obvious gap, no missing piece tugging at the others. The story of the solar system felt closed. Then a small group of astronomers started paying attention to the loneliest objects we know, the ones that swing out far past the Kuiper Belt and take thousands of years to return. These are the extreme distant worlds, and they behave in a way the tidy map cannot explain. Their orbits are not scattered at random, the way loose objects usually are. They seem to be arranged. That arrangement is the thread this whole story pulls on. A few dozen frozen bodies, each smaller than our moon, trace long looping paths that lean and point in nearly the same direction. Imagine a handful of clock hands spread around a room, all somehow drifting to point the same way. Something has to be holding them there. On Earth, when things line up like that, we look for the force behind the line. The simplest force is gravity, and the simplest source of gravity is mass. So the question wrote itself into the sky. If those distant orbits are being held in line, what is holding them, and where is it hiding? One answer, the boldest one, is that a real planet is out there, unseen, far beyond everything we have mapped. Not a myth, and not a moon, but a world several times heavier than Earth, moving through the dark on an orbit so wide it has never once been photographed. That world has a plain name. Astronomers call it Planet 9. Whether it truly exists is one of the great open questions in our own backyard, and the rest of this journey is the search for it, step by careful step, from the first faint clue to the newest and most unsettling one. The first real clue arrived quietly, in 2014, in a paper about 2 very distant objects. The astronomers were Chad Trujillo and Scott Shepard, and they were not hunting a planet. They were studying the far frontier of the solar system, the region past the Kuiper Belt where only a few icy worlds have ever been found. One of those worlds was Sedna, discovered a decade earlier. Sedna is a reddish ball of ice on an orbit so stretched that even at its closest it stays far beyond Neptune. It never comes near the known planets. Nothing we can see reaches out to touch it, and yet something must have placed it on that lonely path, because Neptune's gravity, the usual sculptor of the outer system, cannot reach that far. Trujillo and Shepard found a second world like Sedna, an object with the plane catalogue name 2012 VP 113. Some astronomers nicknamed it Biden after the letters in its label. Like Sedna, it swings far out and stays there, detached from Neptune's influence. Two lonely worlds, both stranded in the same empty region, was already a small puzzle. Then the two astronomers noticed something about the shape of these orbits and about a larger set of distant bodies they compared them to. Every orbit has a low point, the place where the object swings closest to the Sun. There is a way to describe the tilt and direction of that closest approach. A number of astronomers call the argument of perihelion. It is simply an angle that says which way the orbit leans as it dips toward the Sun. For scattered, unrelated objects, that angle should be spread all over the place. Some orbits should dip one way, some another, with no pattern at all. That is what randomness looks like. But when Trujillo and Shepard lined up the most distant objects they had, the angles were not spread out. They were bunched together, clustered near the same value, as if the orbits had agreed on a direction. That is a very strange thing to see. These objects are separated by billions of miles. They do not talk to each other. They feel almost no pull from one another. There is no local reason for them to share an angle. And still, there it was. A tidy grouping where the math expected a mess. Trujillo and Shepard were careful in how they said it. They suggested that a large, undiscovered body far beyond the known planets could be shepherding these orbits, keeping their closest approaches lined up. They put a rough size on it, something at least a few times the mass of Earth, sitting a couple of 100 astronomical units out. They did not claim to have found a planet. They pointed at a pattern and named the kind of thing that might cause it. It was a small paper with a large idea folded inside it. The clustering could have been a fluke, an accident of the handful of objects known at the time. There were only a few of them after all, and a few points can line up by chance the way three houses on a street might happen to share a colour. The honest response was caution, but the pattern was suggestive enough to pull other astronomers in and to set two of them at a whiteboard, asking what kind of hidden world could comb the far solar system into these gentle, stubborn lines. That question is where the story turns from a curiosity into a hypothesis. To feel why the clustering matters, it helps to slow down and think about what randomness should look like. Imagine emptying a box of toothpicks onto the floor. They land pointing every which way. No direction is special. That is the natural state of things that do not influence each other. Left alone, the far orbits of the solar system should behave the same way, spread evenly around the Sun with no shared direction. The distant objects do not do this. Their orbits lean together in space, not just in that one closest approach angle from the first clue, but in the full three-dimensional way they sit around the Sun. Astronomers describe this with another plane measurement, the longitude of perihelion, which is the compass direction toward an orbit's closest point. When they plotted those directions for the most distant, most detached objects, the arrows pointed into the same broad slice of sky. There is a second layer to it. The orbits are also tilted in a shared way, their planes leaning in the same sense rather than at random angles. So it is not one coincidence but two, stacked on top of each other. The closest points agree, and the tilts agree. Two independent things lining up at once is far less likely than either one alone. Batygin and Brown later put a number on the chance of this being an accident. In their analysis, the odds that the alignment was pure luck came out to a fraction of 1%. That is not proof, and they were clear about that. But it is the kind of number that makes a scientist stop treating a pattern as noise and start treating it as a clue that needs a cause. Now, there is an honest wrinkle here, and it deserves to be said plainly. We have only found a few dozen of these very distant objects, and finding them is brutally hard. They are faint, they move slowly, and telescopes only search certain patches of sky on certain nights in certain seasons. If you only ever look northeast, you will only ever find things to the northeast, and you might convince yourself the whole world lies in that direction. So part of the apparent clustering might come from where and when we happen to point our telescopes, rather than from anything real in space. This is called observational bias, and it is the ghost that haunts the whole Planet 9 story. Every clustering claim has to answer it. The people who believe in the pattern have tried hard to correct for it, mapping out exactly which parts of the sky each survey could and could not see, and asking whether the alignment survives once that is accounted for. In their work, it does. Critics argue the corrections are not enough, and that with so few objects we simply cannot be sure yet. Both sides are being reasonable. That is worth holding on to. This is not a fight between science and nonsense. It is a genuine disagreement about a small, hard-won pile of data and about how much weight a few dozen faint points of light can bear. But suppose for the length of this story that the pattern is real. Suppose the far solar system truly is combed into line. Then something with real gravity has to be doing the combing, something massive enough to reach across hundreds of astronomical units and hold those orbits in place for the age of the solar system. That supposition is exactly what two astronomers at Caltech decided to chase, and what they built out of it still stands at the centre of the search. The two astronomers were Konstantin Batygin and Michael Brown, both at the California Institute of Technology in Pasadena. They made an unlikely pair for the job. Brown is an observer, a discoverer of distant worlds, the man whose finding of a Pluto-sized object named Eris helped push Pluto out of the Planet Club years earlier. Batygin is a theorist, younger, more at home with equations and simulations than with telescopes. Brown has said they took up the problem partly to prove each other wrong. In 2016, they published the paper that gave the idea its name and its spine. They took the clustering that Trujillo and Shepard had flagged, and they asked a direct question. What single object, on what orbit, could produce this exact pattern and keep it stable for billions of years? Then they did the patient work of testing answers. Their main tool was a computer simulation of the kind astronomers use to model gravity, sometimes called an N-body simulation. The plain version of the idea is this. You place the Sun, the giant planets, and a swarm of distant icy bodies into a computer, along with one proposed hidden planet. Then you let gravity run, step by step, for the equivalent of billions of years, and you watch what happens to the swarm. If your imagined planet is wrong, the swarm scatters into a mess. If it is right, the swarm settles into the pattern we actually see. Batygin ran these worlds forward again and again, changing the hidden planet's mass, its distance, and the shape of its orbit each time. Most versions failed. The distant objects flew apart, or piled up in the wrong place, or lined up in a direction that did not match the sky. But a particular kind of planet, massive and far and riding a stretched tilted orbit of its own, did something remarkable. It gathered the icy bodies into the same leaning clustered arrangement that Trujillo and Shepard had found. There was a twist in the result that made it more convincing, not less. The hidden planet did not line the small orbits up with its own. It did the opposite. It settled them into an anti-aligned state, meaning the small worlds swing closest to the Sun on the far side from where the big planet does. Picture a heavy runner on a track holding a crowd of lighter runners in a loose formation on the opposite curve, never letting them drift. That anti-alignment is a subtle behaviour, hard to produce by accident, and it fell out of the simulations naturally. That was the moment the idea stopped being a vague suggestion and became a specific claim. Not merely that some big thing might be out there, but that a particular planet, of a particular mass, on a particular sort of orbit, could explain the data in one clean stroke. Brown, the man who had helped unmake one planet, was now arguing for a new one. They called it Planet 9, and they were careful with the word. They did not say they had discovered a planet, they had discovered a solution, a set of numbers that made the strange sky make sense. The planet itself remained unseen. It was an inference, a shape cut out of the darkness by the things it seemed to be moving. The paper landed hard. It was the first time in modern astronomy that a serious testable case had been made for a large new planet in our own solar system, built not on a single strange object, but on the shared behaviour of many. And it came with a challenge attached. If the planet was real, it was somewhere out there to be found. Someone only had to look in the right place, with a telescope strong enough to catch it. So what did the ghost look like on paper? Batygin and Brown gave it a rough shape, and over the years that shape has been sharpened and argued over, but the first sketch is worth picturing. They estimated Planet 9 at roughly 10 times the mass of Earth in their earliest work, a value later trimmed towards something more like 5 or 6 Earth masses as the models improved. That range makes it a particular kind of world. It is far heavier than Earth, but much lighter than Neptune. Astronomers call this in-between class a super-Earth or a mini-Neptune, and it is one of the most common types of planet we have found around other stars, yet we have none of it in our own system. If Planet 9 exists, it fills a gap in our own family that we did not know was empty. Then there is the distance, which is the part that stops you. In the first paper, they placed it near 700 astronomical units from the Sun. Remember that 1 astronomical unit is the Earth to Sun distance, and that Neptune sits at about 30. So this planet would orbit roughly 20 times farther out than Neptune, and hundreds of times farther than we are. Later analyses pulled that estimate inward, toward a few hundred astronomical units. But even the closer numbers are staggering. Sunlight, which reaches Earth in about 8 minutes, would take days to crawl all the way out to Planet 9. Its orbit is not a neat circle, it is stretched into a long oval, what astronomers call an eccentric orbit, so that the planet spends part of its enormous year closer in and part of it flung much farther out. It is also tilted, leaning against the flat plane where the other planets run, and it is slow beyond easy imagining. 1 trip around the Sun would take something like 10,000 to 20,000 years. A single Planet 9 year is longer than all of recorded human history. When the last ice age gripped the Earth, this world had not yet finished the orbit it may be on now. Put those numbers together, and you get a picture of why it has never been seen. It is small compared to the giant planets, so it is not a huge target. It is fantastically far, so what light it does throw back at us is feeble, and it moves so slowly that from night to night it barely shifts against the background stars, which is exactly the motion that would give it away. A planet that creeps is a planet that hides. There is one more feature worth holding in mind, because it becomes important later. The predicted orbit is not just far and stretched. It is tilted at a modest angle, something like 15 to 30 degrees away from the plane of the other planets. That is enough to be interesting, but not extreme. The planet in the standard picture leans against the family table without standing up entirely from it. Keep that gentle tilt in mind. When a real candidate finally turned up, the first thing anyone checked was whether its tilt matched, and the answer would reshape the whole story. For now, hold the sketch as a whole. A world several times Earth's mass, dark and cold, on a long, slow oval that carries it hundreds of times farther from the Sun than we are, tilted just off the plane of everything we know. That is the thing Batygin and Brown argued into being. The next question is the one that keeps astronomers up at night. If it is out there, how does something so far away reach back across all that emptiness and hold a swarm of distant worlds in line? Here is the strange heart of the idea. Planet 9, if it exists, controls a crowd of objects it never comes near. It does not bump them or catch them. It rules them from a distance through nothing but gravity and time. Gravity is patient. The pull between 2 far apart objects is weak, but it never switches off. Give it thousands of years, then millions, then billions. and even a faint tug repeated on every orbit can steer a small world into a new path. Planet 9 works on the distant icy bodies the way a slow current works on driftwood. No single moment moves the wood far. The current just never stops. The way it steers them is through a set of rhythms astronomers call resonances. A resonance is a simple timing relationship between two orbits. When one object goes around the Sun a whole number of times for every so many trips of another, the gentle gravitational nudges between them fall in the same places again and again, and small effects add up instead of cancelling out. It is the same reason a child on a swing goes higher when you push in time with the swing rather than at random. Push with the rhythm, and the effect grows. Planet 9 in this picture pushes the distant objects in rhythm over and over across the age of the solar system. Over that vast stretch of time, these repeated nudges do two things at once. They keep the closest points of the small orbits lined up in the same region of sky, and they keep the orbital planes leaning the same way. That is the double clustering we met earlier, the closest points agreeing and the tilts agreeing. The simulations show that a distant, massive, eccentric planet naturally locks the swarm into this shape and holds it there, replacing chaos with quiet order. The anti-alignment we mentioned is part of this. The small worlds are shepherded so that they reach their closest approach to the Sun on the opposite side from where Planet 9 reaches its own. That opposition is stable. If one of the little worlds drifts out of step, the gravitational rhythm nudges it back. The arrangement corrects itself, the way a marble settles into the bottom of a bowl even if you jostle it. There is a way to test whether this is more than a nice story, and Batygin and Brown leaned into it. If a real planet is doing the shepherding, then it should not only hold the known objects in line, it should also create whole populations we would not otherwise expect. In particular, the same gravity that lines up the distant orbits should, over time, kick some objects up and out of the flat plane of the solar system entirely, onto steeply tilted or even backward paths. We have found objects like that. There are distant bodies that orbit the Sun almost sideways to the planets, and a few that go around the wrong way, against the general spin. These are hard to explain with the ordinary machinery of the outer solar system, but they fall out naturally when you add a Planet 9 to the simulation and let it run. The same hidden hand that combs the swarm into line also flings a minority of worlds out of the plane. One cause, two very different effects, both matching what we see. That is the quiet power of the hypothesis. It does not just explain the clustering it was invented for, it reaches sideways and accounts for other oddities that were never part of the original puzzle. A good idea in science tends to pay for itself twice. Planet 9, at least on paper, does exactly that, which is why so many people are unwilling to let it go, even now. Come back to Sedna, because it is the clearest window into all of this. Sedna is a distant, reddish world discovered in 2003 by a team that included Michael Brown, years before Planet 9 had a name. It is smaller than our moon, coated in ancient sun-darkened ice, and it follows one of the loneliest paths we know. What makes Sedna special is not how far it goes at its farthest. Plenty of comets swing out to enormous distances. What makes Sedna strange is how far it stays even at its closest. Its nearest approach to the Sun, the low point of its orbit is around 76 astronomical units. That means Sedna never comes closer to the Sun than about 2.5 times Neptune's distance. It lives permanently in the deep outer dark. That single fact is a real problem for the tidy solar system. In the standard story, the outer worlds get their stretched orbits from close encounters with the giant planets, especially Neptune. Neptune flings a small body outward, giving it a long looping path, but that path still dips back down near Neptune where the encounter happened. Sedna's low point is far beyond Neptune's reach. Neptune could not have placed it there. Something else did. Something that has since gone missing or hidden. Astronomers call worlds like this detached objects because they are cut off from the influence of the known planets. When a detached object also has a very large orbit, it earns a nickname among researchers, a sednoid, after Sedna itself. There are only a handful of them. Alongside Sedna sits the object labelled 2012 VP113, with a closest approach even farther out, around 80 astronomical units. A few others have joined the small club since. These sednoids are the crown jewels of the Planet 9 case, because they are the hardest to explain any other way. You need a force that can lift a small world's closest approach far above Neptune and then leave it stranded there, stable, for billions of years. A large distant planet does exactly that. As it shepherds the swarm, it can raise the low points of some orbits, detaching them from Neptune and parking them in the deep. Sedna, in this reading, is not an oddball, it is a footprint. It helps to picture the scale of Sedna's world. Standing on its surface, you would find the sun shrunk to a fierce point of light, bright enough to hurt the eye but far too small to warm anything. Daylight would look like a very sharp dusk. The temperature would sit near the coldest anything gets, close to the point where even nitrogen would freeze solid, and the sky would barely change from year to year, because Sedna takes something like 11,000 years to circle the sun once. A civilization could rise and fall on Earth in the time it takes Sedna to complete a single lap. Sedna is also a reminder of how thin our knowledge is out here. We only found it because for a brief window in its long orbit, it happens to be near its closest point, and therefore bright enough to catch. For most of its 11,000-year year, it is too far and too faint for our telescopes to see at all. There may be many more sednoids out there, spending almost all their time in the unreachable dark, invisible to us now. Each one we do find is another data point in the clustering, another orbit to check against the pattern, and every so often, a new one turns up that does not fit as neatly as hoped, which is a tension we will come back to. The clustering and the sednoids are the main evidence, but supporters of Planet 9 point to a few other fingerprints, softer marks that the same hidden hand might have left. The first involves the Sun itself. The planets all orbit in a fairly flat sheet, like marbles rolling on a tabletop. You might expect the Sun to spin in line with that sheet, its equator matching the plane of its family. It does not quite. The Sun's spin is tilted by about 6 degrees relative to the plane of the planets. That is a small angle, but it is real, and it has puzzled astronomers for a long time. Why should the Sun lean away from the very disk it was born with? One proposed answer is Planet 9. A massive planet on a tilted, distant orbit tugging on the whole planetary system for billions of years could slowly torque that flat sheet, tipping it a few degrees relative to the Sun. In this picture, the modest lean of the Sun is not a leftover accident from birth, but a signature, the long, patient pull of a hidden world showing up as a tilt in the entire solar system. It is a bold claim, and not the only explanation on offer, but it fits. The second fingerprint is the family of objects that orbit at steep angles. Most things in the outer solar system move in roughly the same flat plane as the planets. A few do not. There are distant bodies on paths tilted far out of that plane, and a small number that orbit almost perpendicular to it, rising and falling steeply like a ball tossed over a fence. A couple of these have been given informal names by the researchers who study them. These high-tilt objects are awkward to produce. The ordinary machinery of the outer solar system, dominated by Neptune, tends to keep things flat. To lift a world onto a steeply tilted or perpendicular orbit, you need a persistent push from something outside that flat machinery. When Batygin and Brown ran their simulations with a Planet 9 included, these steep orbits appeared on their own, generated by the same gravitational rhythms that align the clustered swarm. The planet that combs most orbits into line also flips a few of them onto their edges. Later work by Batygin and Brown in 2024 added another layer. They looked at a population of more ordinary objects, the ones that do cross near Neptune's orbit, and argued that Planet 9's gravity helps explain how those orbits are fed and sustained over time. In their analysis, a solar system with no Planet 9 failed to reproduce the observed mix at a high level of statistical confidence. A solar system with one matched better. That is the kind of quiet, cumulative argument that rarely makes headlines but slowly moves expert opinion. None of these extra fingerprints is decisive on its own. The Sun's tilt has other possible causes. The steep orbits are few, and small numbers are always shaky. The Neptune crossing argument depends on models that critics can question. Take any one of them alone, and a careful scientist would shrug. But supporters argue that the case is not meant to rest on any single leg. It is meant to rest on the way several independent oddities, the clustering, the sednoids, the tilt of the Sun, the perpendicular worlds, all point in the same direction, toward one simple cause. That is the strongest version of the argument, and it is genuinely compelling. It is also, so far, entirely circumstantial. Every piece of it is a shadow cast by the planet, never the planet itself. And shadows, as the skeptics keep reminding everyone, can be thrown by more than one kind of thing. Before we meet the skeptics, though, we have to face the plainest obstacle of all. Why, after 10 years of looking, has no one simply seen it? The obvious way to settle the whole question is to point a telescope at the sky and find the planet. It sounds simple. It has turned out to be one of the hardest searches in modern astronomy, and the reason comes down to a cruel piece of arithmetic about light. A planet does not shine on its own. It glows only by reflecting sunlight, the way the moon does. So to see Planet 9 in ordinary visible light, sunlight has to travel all the way out to it, bounce off its surface, and travel all the way back to our telescopes. Both legs of that journey drain the light, and they drain it fast. Here is the plain version of the arithmetic. The brightness of sunlight falls off with the square of the distance. Go twice as far from the Sun, and the light is 4 times fainter. That already thins the sunlight, reaching a distant planet to almost nothing. But then the reflected light has to come back to us, and it fades by the square of the distance again on the return trip. Multiply those two together, and the light we finally receive from a distant planet drops off with the 4th power of its distance. Move a planet twice as far away, and it becomes 16 times harder to see, not 4. Now apply that to Planet 9. It may sit hundreds of times farther from the Sun than the Earth does. Raised to the 4th power, that distance turns the reflected light into a whisper. Batygin and Brown estimated that the planet, if it exists, would be extraordinarily faint, near the very edge of what our largest survey telescopes can detect, and fainter still when it is near the far end of its long orbit. It would be a dim, slow, easily missed speck, lost among countless faint stars and galaxies that do not move. That last part matters. The sky is crowded with faint points of light, and almost all of them are stars and galaxies far outside the solar system, which hold still from night to night. The only thing that gives a planet away is its motion against that fixed background. But Planet 9 moves so slowly, creeping along its enormous orbit, that over a single night it barely budges. You cannot catch it in one glance. You have to photograph the same patch of sky on different nights, sometimes weeks or months apart, and hunt for the one faint dot that has shifted by a hair while everything else stayed put. To make it worse, we do not know exactly where to look. The predicted orbit covers a huge arc of sky, and the planet could be anywhere along it. It is most likely to be near the far, slow end of its orbit right now, simply because a planet spends most of its time out there where it moves slowest, like a stone lingering at the top of its arc. That is also where it is faintest and hardest to find. The most probable place to look is the worst place to see it. So the search is not a matter of aiming a great telescope and waiting for the planet to appear. It is a matter of surveying enormous stretches of sky, again and again, and combing through millions of faint specks for the rare one that moves the right amount in the right direction. It is slow, patient, unglamorous work, and for years it produced only silence, or rather, it produced a growing list of places where the planet was not. That silence is important. To understand what the recent infrared clue really means, and why it caused such a stir, we first have to see how thoroughly the ordinary hunt had come up empty. For a decade after the 2016 paper, astronomers hunted Planet 9 in visible light with the biggest survey tools they had, and the hunt kept coming up empty in a useful way. Michael Brown and Konstantin Batygin did much of this searching themselves, turning their own prediction into a target. They used the Zwicky Transient Facility, a wide-field camera in California that scans large swathes of sky quickly, well suited to catching things that move or change. They combed through its data for a slow, faint mover, matching the planet's expected brightness and pace. They did not find it, but they were able to say with confidence that the planet was not in the parts of the sky and the range of brightness that survey could reach. That is the quiet logic of a null result. Every search that fails still teaches you something, because it crosses territory off the map. If you have lost your keys in the house, every room you search and clear brings you closer to the room where they must be. Brown began keeping a running tally of how much of the possible hiding space had been ruled out, and over the years that fraction climbed. By some of his estimates, most of the likely sky had been checked and cleared, narrowing the search to a smaller and smaller corner. Other great surveys joined the effort. The Dark Energy Survey, run with a large camera in Chile, had mapped a wide region of the southern sky for an entirely different purpose, to study the expansion of the universe. Astronomers realized that same data could be searched for a slow-moving planet, and teams including Brown students pored over it. Again, no Planet 9, but more of the map cleared. Phan stars, a survey based in Hawaii that had already discovered a great many distant solar system objects, was searched in the same spirit, ruling out further ground. Then there is Subaru, a large telescope on Mauna Kea in Hawaii, with a wide-field camera called Hyper Supreme Cam, well matched to hunting faint distant worlds. Subaru has been one of the most productive tools for finding new outer solar system objects, the very sednoids and clustered bodies that feed the Planet 9 case. It has also been used to search directly for the planet in the most promising patches of sky. Its power is real, but even Subaru can only cover so much sky so deep, and Planet 9 kept not appearing. By the early 2020s, the situation had a strange shape. The circumstantial case for Planet 9 was as strong as ever, arguably stronger, as new clustered objects turned up and the models improved. Yet direct searches had swept much of the likely sky and found nothing. The planet was becoming, in a phrase some astronomers used, a world that was running out of places to hide. That could mean two very different things, and honest scientists held both. It might mean the planet is real, and simply lurks in one of the few remaining unsearched corners, most likely the faint far end of its orbit where it is hardest to catch. Every cleared region made that remaining corner more specific, and in a sense the search more hopeful, because it was closing in. Or it might mean the planet is not there at all, and the clustering has some other cause, and the searches are empty because there is nothing to find. Visible light alone could not break the tie. The planet, if it existed, was too dark in reflected sunlight, and the unsearched corners were exactly the hardest ones. To make progress, astronomers needed either a far more powerful survey of the whole sky, which was coming, or a completely different kind of light to look in, which was already sitting in old archives, waiting. Both paths lead into the rest of this story. It would be dishonest to tell this story as if everyone believes in Planet 9. Many serious astronomers do not, and their doubt is not stubbornness. It rests on the same weakness we met earlier, the ghost of observational bias. The whole case begins with the clustering of distant orbits, but that clustering was found using telescopes that could only look at certain parts of the sky, on certain nights, in certain seasons, from certain places on Earth. If the searches themselves favoured one region of the sky, then the objects we found would naturally seem to gather there, even if the real population is spread out evenly. The pattern might live in our observing schedule rather than in space. To test this, a large international project called the Outer Solar System Origin Survey, usually shortened to OSOS, took a careful approach. Instead of scanning wherever seemed promising, the team mapped out in advance exactly which patches of sky they searched and how sensitive each search was. That way, they could correct for their own bias with precision. When they analysed the distant objects they found this way, the striking clustering did not clearly appear. Their objects looked consistent with a fairly even distribution, once the survey's own tilt was accounted for. The Dark Energy Survey, mentioned earlier for its hunt, also discovered many new distant objects, and analyses of that well-characterised sample likewise struggled to see convincing clustering. Two of the most carefully controlled searches, in other words, did not strongly confirm the pattern that Planet 9 was invented to explain. Astronomers like Samantha Lawler at the University of Regina have argued this point clearly. In her view, the apparent alignment of the distant objects is most likely a mirage produced by biased observations of what is really a uniform swarm. If that is right, then there is no pattern to explain, and no need for a hidden planet at all. Others, including planetary scientists who study these populations closely, share a version of that caution. Earlier work by researchers such as Corey Shankman working with the OSOS data reached similarly skeptical conclusions. Batygin and Brown have pushed back, and this is where it gets genuinely hard for an outsider to judge. They argue that when you account for bias properly, using all the available objects and the most complete maps of where surveys looked, the clustering does survive at a level unlikely to be chance. They have refined this argument repeatedly. The skeptics counter that the samples are still too small and the corrections still too uncertain to bear the weight of a whole new planet. The honest summary is that this is an open dispute among careful people, driven by a shortage of data rather than a shortage of rigour. Both camps agree on the raw facts. There are a few dozen very distant objects. They're extremely hard to find, and our searches have been uneven. What they disagree about is whether the apparent order in those orbits is real signal or clever noise. That is a subtle question, and subtle questions in science usually wait for better data rather than better arguments. This matters for everything that follows, because it frames how to read any new clue. When a faint candidate turned up in old infrared data, or when a fresh distant object was discovered, the first reaction of the field was not celebration. It was a careful, almost wary checking. Does this help the pattern, or hurt it? Does it fit the predicted planet, or point somewhere else entirely? The skeptics have trained the whole community to ask those questions before getting excited. And as it happens, the newest clues have not simply confirmed the planet. Some of them have pointed in directions no one expected, including a couple that seem to argue against the very idea they were meant to support. Before we reach those, we should look at the other suspects, the things that are not a planet at all. Suppose the clustering is real, and something massive out there is shaping those orbits. It still does not have to be a planet. Over the years, astronomers have floated several stranger suspects, and taking them seriously is part of doing the problem honestly. The most dramatic is a small black hole. In 2020, physicists Jakob Schultz and James Unwin proposed that the gravitational pull attributed to Planet 9 might instead come from a primordial black hole, a tiny black hole left over from the earliest moments of the universe. Such an object, if it had a mass of 5 to 10 times the Earth, would be a bizarre thing. It would be smaller than a grapefruit, a point of collapsed matter, and yet it would carry the gravity of a super-Earth. Our solar system, in this idea, might have quietly captured one long ago, and it would be tugging the distant orbits exactly as a planet would. It is a wonderful and unsettling thought. A black hole orbiting in our own solar system, invisible not because it is far and dark, but because it is almost nothing at all. And because gravity does not care what produces it, the black hole would pull on the sednoids in the same way a planet would. From the orbits alone, you could not tell the difference. That is why the idea could not simply be waved away. A gentler suspect is not one object but many. Instead of a single hidden planet, perhaps the outer solar system holds a broad, faint disk of small, icy bodies, a great ring of debris whose combined gravity does the shepherding. If enough mass is spread out there in countless small pieces, the whole disk together might nudge the distant orbits into their aligned pattern, with no single large world required. This idea has the appeal of not inventing a new planet, though it has its own difficulties, since such a massive disk should leave other marks we have not clearly seen. The most radical suspect throws out the hidden mass entirely. A small group of physicists has asked whether the strange orbits might be a sign that gravity itself behaves slightly differently at very large distances than our standard equations predict. This family of ideas, known broadly as modified gravity, was originally invented to explain the motions of whole galaxies without invoking dark matter. A few researchers have wondered whether a version of it could reshape the far solar system too, mimicking the pull of a planet that is not there. This is very much a minority view, and most astronomers doubt it, but it exists on the edge of the conversation. For a while, the suspects sat side by side with the planet as live possibilities, and there was no clean way to choose between them from the orbital data alone, since gravity from a planet, a black hole, or a disk can all look the same in the paths of distant worlds. This is exactly why the recent infrared clue is so interesting, and it quietly rules one suspect out. A planet is cold, but it is not nothing. It has a solid body with a temperature, and a body with a temperature glows faintly in infrared light in its own heat. A tiny black hole of the same mass would not glow that way at all. So if a real, heat-emitting object turns up in the predicted region, that alone argues against the black hole idea. Whatever is out there, if the infrared dot is real, it has a surface and a warmth. It is the kind of thing you could, in principle, stand on. That shifts the search onto new ground. Rather than only tracing gravity through the orbits of other worlds, astronomers could try to catch the object's own heat directly. And to do that, they did not need a new telescope. They needed old data, taken long ago for entirely different reasons, and never fully searched. The trick behind the newer search is a switch in the kind of light we look for. Instead of hunting the sunlight a planet reflects, you hunt the light it makes on its own, its heat. Every object with a temperature above the coldest possible cold gives off light. You do this yourself. Your warm body glows in infrared, a kind of light just past the red end of what your eyes can see, which is why night vision cameras can spot you in the dark. Hot things glow in visible light, like the filament of an old bulb. Cooler things glow in infrared instead. The colder the object, the longer and more stretched out the light waves it sends out. Astronomers call this heat glow thermal radiation, and it depends only on how warm a thing is, not on any sunlight falling on it. Planet 9 would be desperately cold, but not perfectly so. Estimates put its temperature somewhere in the range of a few tens of degrees above absolute zero, the true bottom of the temperature scale. That is colder than anything in everyday life, cold enough to freeze the gases we think of as air. But it is not zero. A world that cold still glows, faintly, in the far infrared, the long wavelength part of that heat light. It carries its own small candle of warmth, left over from its formation and from the trickle of energy inside it. Now recall the cruel arithmetic that made visible light searches so hard. Reflected sunlight fades with the fourth power of distance, because the light makes two trips, out and back, each fading with a square of distance. Heat light is different. The planet's own glow only has to make one trip, from the planet to us, so its brightness falls off with just the square of the distance, not the fourth. For an object hundreds of times farther than the Earth, that difference is enormous. In its own heat, a distant planet is far less hopelessly faint than it is in borrowed sunlight. There is a second gift. The universe is full of faint stars and galaxies that shine in visible light, and they clutter every optical search. But a cold planet's far infrared glow peaks at wavelengths where those distant stars are dim and where fewer things compete. The kind of light Planet 9 would give off is not the kind most other objects shine brightly in. In the right infrared band, a cold, nearby world can stand out against a quieter background. Put those two advantages together, and the far infrared looks almost tailor-made for finding a cold, distant planet. This is not a new realization. For years, astronomers had suggested that infrared surveys, and even microwave detectors built for other purposes, might catch Planet 9's warmth where visible telescopes had failed. Earlier searchers had already combed some infrared data and turned up possible hints, though none held up as a clear planet. The catch is that scanning the whole sky in the far infrared is difficult and expensive. Infrared telescopes have to be kept extremely cold themselves, chilled with liquid helium, so their own warmth does not blind them and that coolant runs out. As a result, full infrared maps of the entire sky are rare. Only a few have ever been made by satellites that flew years apart, each freezing a picture of the infrared sky for a short window before their coolant was gone. That rarity turns out to be the key to the whole method, because if you have two such all-sky infrared maps taken many years apart, you have something powerful. You have two snapshots of the same sky, separated by enough time that a slow distant planet would have shifted between them. And it happened that we had exactly two such maps, taken 23 years apart, sitting quietly in the archives. The first of those two maps came from a satellite called IRAS, the Infrared Astronomical Satellite. It launched in 1983, a joint effort by the United States, the Netherlands and the United Kingdom, and it changed astronomy in less than a year of work. Before IRAS, the infrared sky was almost unknown territory. The problem was the Earth's own atmosphere, which absorbs most infrared light before it reaches the ground, and the warmth of the telescopes themselves, which drowns out the faint heat of distant objects. To see the infrared sky clearly, you have to get above the atmosphere and chill your instrument to near the coldest possible temperature. IRAS did both. It carried a telescope cooled with liquid helium to just a few degrees above absolute zero, riding in orbit above the blurring, glowing air. For about 10 months, until its coolant ran out, IRAS swept the sky and built the first infrared map of nearly the whole heavens. It was a revelation. It found vast clouds of warm dust threaded through our galaxy, disks of debris around other stars that hinted at forming planetary systems, and countless glowing sources no one had catalogued before. It saw the universe in its own heat for the first time, and much of modern infrared astronomy grew from what it returned. Buried in that flood of data were the faint heat signatures of everything warm enough to glow in the infrared and bright enough for IRAS to catch. Most of those sources were stars, galaxies, and clouds of dust. But in principle, a cold planet in our own outer solar system, glowing faintly in its own warmth, could have been recorded too, as a single dim point among the millions. At the time, no one could pick it out. There was no way to tell a distant planet from any other faint dot in a single snapshot. A planet only reveals itself by moving, and one map holds no motion. So the IRAS data became an archive, a frozen picture of the infrared sky as it looked in 1983. It was studied for decades, mined for stars and galaxies and dust, and its catalogues were refined and republished as computers improved. Somewhere in those long lists of infrared sources, if Planet 9 was real and warm enough and in the right place, its heat might have been quietly logged, mislabeled as just another anonymous point of light. That is the strange thing about a great survey. It captures far more than anyone can interpret at the time. The data outlives its first purpose. A map made to study dust and galaxies in the 1980s could hold, undetected, the fingerprint of a planet no one would seriously predict until decades later. The information sat there the whole time, waiting for someone to ask the right question of it. But one map, however rich, cannot find a slow-moving planet on its own. To catch motion, you need a second picture of the same sky, taken far enough apart in time that a distant, creeping world would have shifted to a new position. In 1983, that second map did not exist. IRAS had taken the first infrared portrait of the sky, and then it fell silent, its helium gone, leaving a single frozen frame. For more than 20 years, that frame stood alone. The infrared sky had been mapped once, but not again at the same full-sky scale, so there was nothing to compare it against. A planet might be sitting in the IRAS catalogue, but with only one epoch of data, it was indistinguishable from the fixed stars around it. The method needed a partner map, and it would take another spacecraft and another generation of technology to make one. The partner map came from Japan 23 years later. In 2006, the Japanese space agency launched an infrared satellite named AKARI, a word that means light in Japanese. Like IRAS before it, AKARI carried a telescope chilled with liquid helium and set out to survey the whole sky in infrared, but with more modern detectors and sharper vision. AKARI observed the sky in several infrared bands, including far infrared wavelengths well suited to catching very cold things. Those long wavelength bands matter for this story, because they cover exactly the range where a frigid, distant planet would glow brightest. Where IRAS had made the first rough infrared portrait of the heavens, AKARI made a cleaner, more detailed one, and it did so during roughly a year and a half of full operation before its coolant too ran low. Now think about what we suddenly had. 2 maps of the entire infrared sky, one from 1983 and one from 2006 and 7. 2 snapshots of the same heavens, taken 23 years apart. For almost everything in the sky, the 2 maps would agree. Stars and galaxies are so far away that they do not visibly move across the sky over a human lifetime, let alone 23 years. Compare the 2 maps, and the fixed stars sit in the same places on both. But a planet in our own outer solar system is different. It is close enough, cosmically speaking, that it drifts. Even a world hundreds of times farther than the Earth would inch along its orbit, and over 23 years it would shift by a small but measurable amount against the fixed background. The predicted motion for Planet 9 works out to only a few arc-minutes per year, an arc-minute being a tiny slice of sky about the width of a coin seen from many meters away. Slow, yes, but across 23 years that slow creep adds up to a shift large enough to notice if you know exactly how to look. This is the heart of the method, and it is beautifully simple. Take the IRAS map from 1983, take the AKARI map from 2006, lay them over each other. Nearly every source will line up, star on star, galaxy on galaxy, because the distant universe holds still. But a cold, slow planet would not line up. It would appear at one spot in the older map and at a slightly different spot in the newer one, having crept a small distance in the intervening decades. Find a faint infrared source that sits in one map and has moved to a nearby position in the other by just the right amount, and you may have found a planet. There is a subtlety that makes the real search trickier than that clean picture. A distant planet does not only drift along its orbit. Because the Earth swings around the Sun each year, our viewing angle shifts, and a nearby object appears to wobble slightly over the course of a year, an effect called parallax. It is the same reason a nearby finger seems to jump against the far wall when you look with one eye and then the other. For a distant planet, this yearly wobble is small, but it means the object would sit still over a few hours and then shift over months, a distinctive rhythm the search could look for. So the pieces were all in place. 2 all-sky infrared maps decades apart in the right wavelengths, holding the fixed stars steady and any slow planet as a telltale mover. The data had existed for years. What remained was for someone to do the enormous careful work of actually combing through it, source by source, to find the one dot that had moved. That work fell to a small team led by a young astronomer in Taiwan. The design of the search turned on a clever reading of how a distant planet would behave in the AKARI data, and it is worth walking through slowly because the cleverness is the whole point. AKARI scanned the sky in strips, revisiting each part of the heavens several times. For an ordinary fixed source, a star or a galaxy, this was simple. The object showed up in the same spot every time AKARI looked, over hours, over days, over the whole mission. So the standard AKARI catalogue, the reliable one used for most astronomy, only kept sources that were confirmed again and again in the same place. Anything that appeared once and then was not seen at that spot later was treated as unreliable and set aside. But think about how a distant planet would behave. Over a few hours it would sit still, because it moves so slowly. So AKARI could catch it in a single set of scans on a given day. Yet over months, two things would move it. Its own orbital creep would nudge it along, and the Earth's yearly swing around the Sun would shift the viewing angle, that parallax wobble. So the planet, unlike a star, would not reappear at the same spot half a year later. By the standards of the reliable catalogue, it would look like an unconfirmed, untrustworthy source, exactly the kind that gets thrown out. This is the insight. The very catalogue most astronomers ignore, the list of sources that showed up briefly and then were not confirmed in the same place, is precisely where a slow-moving planet would be hiding. A planet would be filed under noise. One of the team's own members had built a special version of this list for the AKARI Data, a monthly unconfirmed source list, which kept the sources that appeared over short spans but failed the usual months-long confirmation. Most entries on that list really are junk, cosmic ray hits, and instrument glitches and passing artifacts. But a real planet would look just like them, and would be sitting quietly in that pile. So the search had a plan. Look in the discarded list, the one full of things that did not stay put. Among all that noise, hunt for the rare source that behaves the way a planet should, stationary in a single day's scans but shifted over the long haul. The team also had to know how bright the object should be, so they could ignore anything too faint or too brilliant to be the planet. They worked out the expected infrared glow of Planet 9 by assuming a plausible mass, distance, and temperature, treating it as a cold body radiating its own heat. That gave them a target brightness in the infrared, measured in a unit astronomers use for source strength. They set their detection window around the faint level, where such a planet's heat should land, near the limit of what the surveys could sense. Sources far brighter than that could be dismissed as ordinary warm objects. Sources far fainter could be dismissed as beyond the planet's expected glow. Then came the matter of distance and motion. The team focused on a specific range, imagining a planet somewhere between 500 and 700 astronomical units from the Sun. At that distance, the physics fixed how far the object should appear to shift between the IRAS map and the AKARI map, and how big its yearly parallax wobble should be. That let them calculate the exact separation to look for between a source in the old map and its possible match in the new one. Too small a shift, and it was probably a fixed star. Too large, and it was moving too fast to be a planet that far out. Only a shift in the right narrow band would fit. With the plan set, the target brightness fixed, and the expected motion pinned down, the search became a vast filtering problem. Millions of infrared sources went in one end. The team's job was to let almost all of them fall away and see what, if anything, survived. The person who took on the actual sifting was Terry Long Phan, a young researcher working at National Tsinghua University in Taiwan, together with his colleague and advisor Tomosugu Goto, and a broader team of collaborators in Taiwan, Japan and Australia. Their study, first shared in 2025, is the reason Planet 9 returned to the headlines, and the reason for the word signals in the title of this journey. They began with a staggering amount of data. The infrared catalogues from IRAS and AKARI together held on the order of millions of sources, faint points of heat scattered across the entire sky. Somewhere in that haystack, if the planet was real and warm enough and within their chosen distance range, there might be a single needle, one source that had crept between the two maps in just the right way. The filtering happened in stages, each one throwing away most of what remained. First, they cut out everything that was already known, matching their sources against existing catalogues of stars and galaxies, and removing every point that had a familiar identity. A planet would be a stranger, not something already named and understood. Next, they removed sources in the crowded glowing band of the Milky Way, where the confusion of stars and dust makes faint moving objects nearly impossible to isolate. They cut sources that were too bright or too faint to match the planet's expected infrared glow. They required that the colour of the infrared light, the balance between different wavelengths, be consistent with a cold body rather than a hot star. Then came the crucial step, the one the whole design was built around. For each surviving source in the old IRAS map, they looked for a possible partner in the newer AKARI map, sitting at the small specific distance away that a planet in their target range would have moved across 23 years. They paired old sources with new ones only when the separation between them fell inside that narrow window, the band corresponding to a world roughly 500 to 700 astronomical units out. After all of this automatic filtering, the millions of sources had collapsed to a very short list. 13 candidate pairs remained, 13 cases where a source in the old map had a plausible partner in the new one at the right separation. That was already a remarkable narrowing, from a whole sky of infrared points down to 13 possibilities, but 13 is still 12 too many, and machines make mistakes. So Phan did the unglamorous essential work by hand. He went through the candidate pairs one by one, pulling up the actual infrared images and inspecting them with human eyes. Most of the 13 fell apart under that scrutiny. Some turned out to be noise, the background glowing too brightly to trust. Others were sources that, on close inspection, had not really moved or were not really there in the clean way the automatic search had suggested. He describes most of them turning into false alarms, the ordinary debris of any search through messy data. And that is the honest texture of real astronomy. It is not a single dramatic sighting. It is a long process of doubt, of crossing candidates off, of most promising leads dissolving when you look harder. By the end of that careful inspection, of the 13 pairs the machine had flagged, only one still stood. One candidate survived every filter and every check. One faint pairing, an old infrared dot and a newer one at just the right separation, behaved the way a slow, cold, distant planet should. It was not proof. 2 points of light rarely are, but it was the best single infrared candidate for Planet 9 that anyone had ever pulled out of the sky, and everything about what it might be and what it might not be is where this story turns next. The one that survived is a matched pair of faint infrared dots, one recorded by IRAS in 1983 and one by AKARI in 2006, and the striking thing about it is a kind of absence. In the older IRAS map there is a source at a certain spot. Look at that same spot in the newer AKARI map, and it is gone. Then look a small distance away in the AKARI map, and there is a source, at just the separation a slow planet in the target range should have crept over 23 years. And back at that new position in the old IRAS map, again, nothing. That is exactly the behaviour you would want. A fixed star sits in the same place in both maps. This object does not. It appears in one epoch, vanishes from that spot in the other, and reappears shifted by the right amount. The old dot has no partner where it sits, and the new dot has no partner where it sits, but the two of them, taken together, trace the small step of something that moved. The team looked harder at the AKARI detection in particular, checking how it behaved across the satellite's repeated scans. Recall the plan. A real planet should hold still over a single day and only shift over longer spans. The AKARI source behaved like a slow mover, present in the short-term scans in a way consistent with an object that sits nearly still for hours, rather than a random flicker that appears once and never again. That strengthened the case that this was not simply an instrument glitch, but a genuine, faint, slowly moving body. It is worth being clear-eyed about what this candidate is and is not. It is two detections. 2 points of light, decades apart, that fit the pattern of a single moving object. That is enough to be interesting, enough to survive a careful search that killed 12 other leads, enough to publish and to chase. It is not enough to trace an orbit, or to prove the dots belong to the same body, or to rule out that they are two unrelated faint sources that happen to sit at a suggestive separation. But set the caution aside for a moment and simply take in what it would mean if the two dots really are one world. It would mean that sitting in archives for decades, logged and ignored, mislabeled as unreliable noise, was the heat glow of an unknown planet in our own solar system. It would mean that the warmth of a world no one had ever seen was recorded in 1983, before most people alive today were born, and again in 2006, and that nobody recognised it until a young astronomer went looking in the discard pile with the right idea in mind. That is the quiet drama of the result. Not a telescope swinging to a fresh patch of sky and catching a planet in the act, but a pair of old, patient measurements, taken for other reasons, finally read correctly. The planet, if it is there, didn't hide from us. We simply had not learned how to see what we already had. The next questions are the obvious ones, and the team asked them at once. If this dot is a planet, how big is it, and how far away? The search itself was built around a specific range of masses and distances, so the candidate, by the very design that found it, comes with numbers attached. And those numbers, when you lay them beside the numbers Batygin and Brown predicted years earlier, do something no one quite expected. They do not match as neatly as everyone hoped. Because the search was tuned to a particular range, the surviving candidate arrives already carrying a rough description. The team designed their filter to catch a planet somewhere between 500 and 700 astronomical units from the Sun, with a mass between about 7 and 17 times the Earth. Anything outside that window would have shown the wrong separation between the two maps and been discarded. So the candidate, whatever it truly is, sits inside those bounds by construction. If it is a planet, it is a big one, several to many times the mass of Earth, and it is extraordinarily far, well beyond even the boldest early guesses for Neptune's neighbourhood. Take a moment with that distance, because it is hard to hold. At 500 to 700 astronomical units, this object would be roughly 15 to 20 times farther from the Sun than Neptune. Sunlight, which reaches Earth in about 8 minutes, and Neptune in about 4 hours, would take days to arrive there. From that world, the Sun would be a single brilliant star, the brightest in its sky but giving almost no warmth, one point of light among the others. The idea of a planet bound to our Sun yet sitting that far out, still circling, still held by that faint distant grip, stretches the meaning of the word solar system. The mass range tells its own story. 7 to 17 Earth masses places the candidate squarely in that missing category, heavier than Earth, lighter than Neptune, the super-Earth or mini-Neptune we have found so abundantly around other stars and so far never found around our own. Finding one here, in our own family, would be its own major result, quite apart from the Planet 9 question. It would mean the most common kind of planet in the galaxy had been sitting in our own backyard the whole time, unseen. So on the surface, this looks like a triumph for the hypothesis. A cold, massive, very distant object, glowing in the infrared exactly where a cold, massive distant planet should glow, pulled from the sky by a search designed around Planet 9. The mass fits the general expectation. The distance is on the far side of the predicted range, but not absurd. It would be easy to tell the story as a clean confirmation, the ghost finally caught in its own heat. That is where a careful listener should slow down, because the numbers that matter most are not just mass and distance. An orbit has a shape and a tilt, and it is the tilt that turns this from a confirmation into a puzzle. The two infrared dots do more than say how far away the object is. Combined with the direction and amount of its apparent motion, they hint at how its orbit is oriented in space, whether it lies near the flat plane of the planets or leans steeply against it. Recall the predicted Planet 9. It was supposed to ride an orbit tilted only modestly from the plane of the other planets, something like 15 to 30 degrees, leaning against the family table without standing up from it. That gentle tilt was baked into the whole picture, because it is part of what lets the planet shepherd the distant swarm into the observed pattern. When Michael Brown, the man who predicted Planet 9, took the new candidate's two positions and worked out what orbit could connect them, the tilt he found was not gentle at all, and a planet on that kind of orbit is not the planet he had been searching for. It is something else entirely, which is where the story takes its sharpest and least expected turn. Michael Brown did the natural thing when the candidate appeared. He took its 2 recorded positions and asked what orbit would carry an object from the first to the second in 23 years. There is not one single answer, because 2 points leave room for a family of possible orbits, but he could work out the general character of them, and the character that came out was startling. The orbit implied by the 2 dots is tilted steeply, far more steeply than the planet Brown had predicted. By his calculation, the object would be riding a path inclined something like 120 degrees to the plane of the solar system. An inclination past 90 degrees means the object does not merely lean against the plane of the planets, it orbits the other way, against the grain, in what astronomers call a retrograde orbit, going around the Sun opposite to the direction the planets travel. Sit with how strange that is. The predicted planet 9 leans about 15 to 30 degrees off the plane, moving broadly with the family in the same direction as everything else. This candidate, if the orbit is anything like Brown's estimate, is nearly perpendicular to that plane and running backward. Those are not 2 versions of the same planet, they are 2 completely different worlds on completely different kinds of orbits. So Brown, the co-author of the Planet 9 hypothesis, looked at the best infrared candidate anyone had ever found and said, in effect, "That is not my planet." His words were characteristically plain. The existence of the object, he noted, would not be disproven by this, but whatever it is not the Planet 9 he and Batygin proposed. The tilt is wrong, and the tilt is not a small detail. It is the difference between a planet that could shepherd the distant swarm into the observed pattern and one that could not. This is the twist that most retellings of the story leave out, and it is the honest centre of it. The headline version says a Planet 9 candidate has been found in old infrared data. The truer version says a candidate for some large distant object has been found, and the person who invented Planet 9 looked at it and concluded it is probably not Planet 9 at all. That does not make the candidate boring. If anything, it makes it stranger. A massive cold world on a steeply tilted backward orbit hundreds of astronomical units out would be a remarkable discovery in its own right, a planet whose very existence would demand a new explanation of how it got there. Planets are born from a flat spinning disk, and they tend to inherit its flat forward motion. A large world running perpendicular and backward would be a deep puzzle, a sign of some violent history, a capture or an ejection, or an encounter we have not imagined. Terry Phan, for his part, kept an open and generous view. He acknowledged Brown's point directly. Even if Brown is right that this may not be the predicted planet, Phan noted, they might still have found something, an unknown planet in the outer solar system, which would be its own discovery. That is the scientist's proper stance. You do not need the universe to hand you the exact thing you are looking for. Sometimes it hands you something better, or at least something new, and the right response is to follow it wherever it goes. But there is a deeper problem lurking underneath the mismatched tilt, and it is sharper than simply having found the wrong planet. If this candidate is real, it may not just fail to be Planet 9, it may make the original Planet 9 impossible. Here is the deeper trouble, and it is the reason a discovery meant to confirm a planet could end up unmaking it. 2 large planets in the same distant region of the solar system cannot simply ignore each other. Gravity does not allow polite coexistence between massive worlds on crossing paths. The predicted Planet 9 occupies a certain zone, hundreds of astronomical units out, on a particular kind of tilted forward orbit. The infrared candidate, if real, would occupy a broadly similar distance range but on a wildly different orbit, steeply tilted and running backward. Put both of those massive worlds into the same outer solar system and let gravity run, and they would not leave each other alone. Over the immense stretches of time involved, each would perturb the other. Their orbits would tug and destabilize, and the tidy, long-lived arrangement that the Planet 9 hypothesis depends on would come apart. Brown put the irony gently but unmistakably. A paper that set out to find a candidate for Planet 9, he observed, may really have found something that would show the original idea was wrong the entire time. The two planets could not both be there, stable, for billions of years. So if the infrared object is real and massive and on that backward orbit, it argues against the existence of the predicted Planet 9, because the two cannot share the neighbourhood. That is a genuinely surprising place for the story to arrive. The hunt for Planet 9, using a method built around Planet 9's predicted properties, may have turned up an object whose existence would refute Planet 9. It is the kind of reversal that only real science produces, where the tool you build to catch one thing catches something that undermines the very reason you built it. It is worth being careful here, because the word refute is strong and the evidence is thin. The candidate is 2 dots. Brown's orbit is an estimate drawn from those 2 dots, and a different pair of true positions could imply a different, less extreme orbit. It is entirely possible that with better data the object turns out to be closer to the plane than the first estimate suggested, or turns out not to be a planet at all, or turns out not to be real. Any of those outcomes would dissolve the tension. The refutation is conditional, hanging on a candidate that is itself unconfirmed. But the logic is clean and worth holding, because it shows how tangled the search has become. We are no longer in a simple world where finding the object confirms the theory, and not finding it leaves the theory in limbo. We are in a stranger place, where the most exciting candidate we have could, depending on what it really is, either be a triumph or a quiet demolition. Confirm the object as a planet on a modest forward-tilted orbit, and Batygin and Brown are vindicated. Confirm it as a massive world on a steep backward orbit, and their planet probably cannot exist. Show that it is not real at all, and we are back where we started, waiting. Everything therefore rests on turning 2 dots into an orbit, and 2 dots are simply not enough. To know which story is true, whether this is Planet 9, a rival planet that rules Planet 9 out, or nothing at all, astronomers need to find the object again, and again, and again, until its true path through space is no longer a guess. It cannot be said too often, because the excitement tends to outrun it. 2 dots are not a planet. They are a reason to look harder. Think about what 2 points of light actually give you. They tell you that at one moment, in 1983, there was a faint source here, and that at another moment, in 2006, there was a faint source a little way over there. If those 2 sources are the same object, you can draw a straight line between them and say it moved in that direction at roughly that speed. But an orbit is not a straight line. It is a long curve, and a planet's true path bends as it goes. From 2 points you cannot see the bend. You can only guess at the curve that might pass through them, and many different curves fit. That is why every orbit drawn for this candidate, including the steeply tilted one that caused such a stir, is provisional. It is a best estimate from minimal data, not a measurement. A third detection, at a third time, would begin to reveal the curve. More detections would pin it down. Researchers have noted that something like 9 separate detections are typically needed to nail down a reliable orbit for a distant object like this, and to weed out false matches, we have 2. And there is a more basic doubt beneath even that. We have been assuming the 2 dots are a single moving object. They might not be. The outer solar system and the sky beyond it are littered with faint things. A dim asteroid drifting through the field, a background galaxy, a distant star that happened to be recorded once and not again, a flicker of instrument noise dressed up as a source. Any of these could masquerade as one member of the pair. With only 2 faint detections separated by 23 years, it is genuinely hard to be certain you are looking at one planet twice, rather than 2 unrelated imposters once each. Other astronomers have raised exactly this worry. George Bernstein, a researcher who studies the outer solar system, pointed out how difficult it is to be confident that 2 tiny pinpricks of light at such extreme distances are anything more than noise or a chance pairing of unrelated objects. That is not hostility to the result. It is the ordinary, necessary skepticism that every faint claim must pass through. The people who found the candidate agree with it. Phan and Goto have both said plainly that 2 detections are not enough to determine the orbit, and that follow-up observations are essential before anyone can call this a planet. So the honest status of the infrared candidate is this: it is the best single lead of its kind ever produced, a genuine result from a clever search, worth taking seriously and worth chasing hard. And it is 2 dots, unconfirmed, possibly noise, possibly 2 unrelated objects, possibly a real planet, possibly a planet that would upend the theory that inspired the search. All of those remain live. The candidate has narrowed nothing yet. It has only given the hunt a specific place to point next. The way forward is not more argument, it is more light. You have to find the object again, catch it a 3rd and 4th and 5th time, watch it move, and let the curve of its true orbit emerge from the data. Only then will the dots become a path, and only a path can tell you what this thing is. And while the infrared candidate waited for that follow-up, the sky delivered a separate and independent complication from a completely different search that made the whole picture harder still. While the infrared candidate was drawing attention, a different telescope quietly found something that cut the other way. In 2023, the Subaru telescope in Hawaii, with its wide-field camera, spotted a new distant object. It was given a catalogue label, 2023 KQ14, and later a friendlier nickname, Ammonite, after the coiled fossil shells, a nod to something ancient preserved from an earlier age. Ammonite is a sednoid, one of that rare club of worlds with orbits detached far beyond Neptune's reach, like Sedna and its cousins. Finding a new sednoid is always significant because there are so few of them, and each one is a fresh data point in the clustering that underpins the Planet 9 case. Every time a new distant object turns up, astronomers immediately check the same thing. Does its orbit lean and point the same way as the others, adding to the pattern, or does it break ranks? Ammonite breaks ranks. Its orbit does not align with the other sednoids the way the Planet 9 picture would prefer. Rather than joining the clustered group pointing its closest approach into the same region of sky as Sedna and the others, it sits differently, oriented in a way that does not fit neatly into the aligned swarm. One more object that pointed with the crowd would have strengthened the case. Ammonite pointing its own way weakens it. A simulation study led by Yukun Huang, an astronomer at the National Astronomical Observatory of Japan, examined what Ammonite's orbit means for the hypothesis. The conclusion was cautious but real. The fact that Ammonite does not align with the other sednoids lowers the likelihood of the Planet 9 hypothesis, at least in its standard form. A single distant planet that had been shepherding the swarm for billions of years should have herded Ammonite into the pattern too. That it did not is a mark against the tidy story. This is how science actually erodes or supports an idea, not through one dramatic verdict, but through the slow accumulation of objects that either fit or do not. For years, most newly found distant objects seemed to fit, and the pattern held. Ammonite is a reminder that the sample is small and fragile, and that a single well-measured object pointing the wrong way can chip at a hypothesis built on only a few dozen orbits. When you have so little data, every new piece carries real weight, for or against. It is important not to overstate this either. Ammonite lowers the odds. It does not kill the hypothesis. Supporters can point out that a real planet need not perfectly align every single object, that some scatter is expected, that one outlier among a clustered group is not fatal. The clustering of the others, if it is real, still needs explaining. But the honest reading is that Ammonite made the standard Planet 9 picture a little less comfortable than it was before. So by the time the infrared candidate arrived, the field was already holding 2 kinds of tension. The candidate itself might, if real, refute the predicted planet by its wrong orbit, and Ammonite independently was quietly arguing that the clustering the planet was invented to explain might be weaker than hoped. 2 separate lines of new evidence, neither one a clean confirmation, both nudging toward a more complicated answer than a single tidy Planet 9. Ammonite also carries a hint about what might have happened instead, a possibility that steps away from a currently existing planet and toward the ghost of one that used to be here. What could produce a distant object like Ammonite pointing its own way, if not a planet patiently shepherding it into line right now? One intriguing answer is that the planet responsible is no longer here. It may have existed once, long ago, and then left. Yukun Huang raised exactly this idea. It is possible, he suggested, that a planet once existed in the solar system but was later ejected, and that the strange orbits we see today are the fading echo of its former presence rather than the ongoing work of a planet still in place. In this picture, the outer solar system was rearranged in its youth by a massive world that has since been thrown out into interstellar space, leaving the distant objects on orbits that no longer have a shepherd, slowly drifting out of whatever alignment they once held. This fits something Batygin and Brown themselves have entertained about how a Planet 9, if it exists, might have formed. One leading idea is that the planet did not form far out where it now orbits, but formed closer in, among the giant planets, and was then flung outward by a gravitational kick from Jupiter or Saturn during the chaotic early days of the solar system. A near ejection would leave the planet on a distant stretched orbit, marooned in the cold. A slightly stronger kick would eject it entirely, sending it out of the solar system altogether to wander between the stars. So there are two versions of the same violent story. In one, the kicked-out world stopped just short of leaving and became Planet 9, still bound, still shepherding. In the other, the kick was harder, the world escaped, and what we see now are only the leftover scars, orbits that were sculpted long ago and are now slowly relaxing, with no planet left to maintain them. Ammonite's misalignment is easier to live with in that second version, where nothing is actively keeping the swarm in perfect order because the sculptor is gone. This possibility reframes the whole search in a humbling way. We have been asking where Planet 9 is hiding, but it is possible the honest question is whether there is a planet to find at all, or only the fingerprints of one that departed before humans existed. A search that comes up empty would then not be a failure to find a well-hidden world. It would be evidence that the world is simply not there anymore, and never will be, because it left. There is a strange beauty in that idea. Our solar system may carry, in the orbits of a few faint icy worlds, the memory of a lost sibling, a planet that formed alongside the others and was cast out into the dark. We would be reading a departure written in gravity, an absence shaped like a planet. The clustering, the sednoids, the tilt, all of it could be a kind of fossil, which is a fitting thing to be reminded of by an object nicknamed Ammonite. Of course, this is one hypothesis among several, and not the favoured one. Batygin and Brown still argue the planet is present and findable. Skeptics still argue there is no pattern to explain in the first place. The ejected planet idea sits in between, taking the pattern seriously while doubting that a planet still tends it. Which of these is right cannot be settled by argument. It comes down, as it always does, to going out and looking better and deeper than before. And that is precisely what the follow-up effort and a powerful new telescope were built to do. The first job is the most concrete. Take the infrared candidate, that pair of dots from IRAS and AKARI, and try to find the object again, so its 2 points can become a path. For that, astronomers turn to an instrument already famous for hunting the faint outer solar system, the dark energy camera, usually called DCAM. DCAM is a large, sensitive camera mounted on the Victor Blanco 4-meter telescope at Cerro Tololo in Chile. It was built to study the expansion of the universe, but its combination of a wide field of view and deep sensitivity makes it superb for a very different task: catching faint, slow-moving objects in our own solar system. It has already been used to discover and track many distant bodies, and it can reach objects far too dim for most telescopes. Phan's team pointed to it as the natural tool to chase their candidate. The plan is straightforward in concept and demanding in practice. Use DCAM to image the region of sky where the candidate should now be, given its estimated motion, and see if a faint object of the right brightness is sitting there. If it is, image it again on other nights, watching how it shifts. Each new detection adds a point to the path. The candidate is expected to be extraordinarily faint in visible light, near the limit of what even a powerful telescope can reach, so each observation demands a long exposure, roughly an hour of staring at one patch of sky to gather enough light. It is slow, painstaking work. The goal is to gather enough detections to solve for a real orbit. Recall the rule of thumb that around 9 separate observations are typically needed to lock down a reliable orbit for a distant object, and to be confident you are tracking one body rather than a chance string of unrelated dots. Reach that number, and the guesswork collapses into knowledge. You would know the object's true distance, the shape of its orbit, and, crucially, its real tilt. Whether it lies gently in the plane like the predicted Planet 9, or steeply against it like Brown's estimate suggested. That tilt is what everyone wants. A well-measured orbit would resolve the central tension of the whole infrared story. If the object turns out to lie on a modest, forward-leaning orbit, it becomes a serious Planet 9 candidate after all, and the earlier steep estimate was just the noise of working from 2 points. If it turns out to be steeply tilted and retrograde, it is a different, stranger world, and one whose existence would argue against the predicted planet. And if DCAM looks and finds nothing at all where the candidate should be, that too is informative, casting doubt on whether the 2 original dots were ever a single real object. There is real difficulty in all of this beyond the faintness. The candidate's expected position now carries large uncertainty, precisely because it was derived from only 2 points. A poorly known orbit means a wide search area, and searching a wide area deeply enough to catch so faint an object takes a great deal of telescope time, which is precious and shared among many projects. Finding a needle is hard. Finding a needle when you're not sure which haystack it is in is harder. So the DCAM follow-up is the direct targeted way forward, aimed squarely at the one candidate we have. But there is also a broader, more powerful approach coming, one that does not chase a single dot but sweeps the entire sky again and again, deep enough to catch whatever is out there, planet or not. That approach had been under construction for a quarter century, and just as this story was unfolding, it finally opened its eye. High in the mountains of northern Chile, on a peak called Cerro Pachon, a new observatory has just begun the most ambitious survey of the sky ever attempted. It is called the Vera C. Rubin Observatory, named for the astronomer Vera Rubin, whose work provided the first strong evidence for dark matter, the unseen mass that shapes galaxies. It is fitting that a facility named for her should be built, in part, to hunt for hidden things. At the heart of the observatory sits the Simonyi Survey Telescope, feeding light to the largest digital camera ever built. That camera holds 3,200 megapixels, a resolution so vast that a single image covers an area of sky many times the size of the full moon, in extraordinary detail. The camera is roughly the size of a small car and weighs several tons. Where an ordinary camera captures a scene, this one captures a swath of the universe in one shot, deep and sharp, and then moves on to the next patch a few seconds later. The observatory's great project is called the Legacy Survey of Space and Time, a 10-year campaign to photograph the entire southern sky over and over. The telescope is designed to sweep across the heavens quickly, imaging the whole visible sky every few nights, and then to do it again and again for a decade. The result will be something astronomy has never had, a long time-lapse movie of the universe, showing not just what the sky looks like, but how it changes, night after night, year after year. That capacity to watch for change is exactly what a Planet 9 search needs. A planet reveals itself by moving, and a survey that images the same sky repeatedly is built to catch motion. Over 10 years, Rubin will not just photograph the distant sky. It will track how faint points of light shift, catching slow movers that a single snapshot would miss. If a large cold planet is drifting along an orbit hundreds of astronomical units out, and if it is bright enough in reflected light to reach Rubin's sensitivity, the survey has a real chance of catching it in the act, night after night, until its orbit is plane. The timing gives this story its edge. The observatory released its first images in the middle of 2025, and it formally began its 10-year survey on the 30th of June, 2026, just as the infrared candidate and the Ammonite result were sharpening the debate. After a quarter-century of construction and preparation, the Great Eye opened at almost exactly the moment the Planet 9 question had grown most tangled. The tool that could settle it arrived on schedule, into a field that badly needed a fresh, unbiased look. That word, unbiased, matters. Remember that the deepest doubt about Planet 9 is observational bias, the fear that the clustering is an artifact of where earlier telescopes happened to look. Rubin answers that fear by design. Instead of searching favoured patches, it will survey the whole southern sky uniformly, again and again, mapping exactly what it can and cannot see. A pattern that survives that kind of even, systematic coverage would be far harder to dismiss as a trick of the schedule, and a pattern that dissolves under it would tell the skeptics they were right. So the search now has two prongs. DCAM chases the one infrared dot we have. Rubin scans everything, hunting not just for the predicted planet but for whatever distant worlds are truly out there. To feel why Rubin is such a formidable hunter, it helps to see how it actually works, night to night. The way Rubin hunts is a matter of scale and repetition, and the numbers are hard to believe until you sit with them. The telescope is built to move fast, swinging from one patch of sky to the next in seconds, snapping a deep image, then moving on. Each exposure covers a wide field, and by working through the night without pause, the observatory can sweep across the entire available sky in just a few nights, then begin the cycle again. This is a completely different strategy from pointing a great telescope at one target for hours. Rubin trades depth in a single glance for coverage and repetition. It does not stare, it patrols. And because it patrols the same ground over and over, it builds up for every point in the southern sky, a long record of how that point behaves over time, whether it holds steady, brightens, dims, or moves. To handle a moving sky, the observatory runs an automatic alert system. Each new image is compared against earlier images of the same region, and anything that has changed, appeared, vanished, brightened, or shifted position triggers an alert. These alerts go out to the world within about a minute of the observation. The volume is staggering. Rubin is expected to generate up to 10 million alerts every single night. A flood of notices about everything in the sky that is doing something. Most of those alerts are not planets. They're exploding stars in distant galaxies, variable stars that pulse in brightness, asteroids in the inner solar system streaking along, and countless other changing things. Buried in that torrent, a slow-moving distant world would announce itself as a faint source that shifts position by a tiny amount from one visit to the next, in the particular slow way that marks something far out in our own solar system. The challenge is not a shortage of data. It is finding the rare meaningful signal in an ocean of it, which is a task for sophisticated software and machine learning as much as for human eyes. There are real obstacles, and the observatory's team is candid about them. One is the growing swarm of communications satellites in low orbit around the Earth, which streak bright trails across long exposure images and can mask faint sources beneath them. Engineers are building software to detect and mask those streaks without throwing away good data, but for a target as faint as a distant planet, even a little extra interference matters. Another obstacle is simply the volume. Sorting 10 million alerts a night, every night, for a decade, and reliably flagging the handful that might be a new distant world is a computing problem as much as an astronomy one. But the power is genuine and it is aimed well. For the specific job of catching faint, slow, distant objects, Rubin's combination of a wide field, deep sensitivity, and relentless repetition is better matched than anything that came before. Where earlier surveys checked patches and moved on, Rubin will map the whole southern sky uniformly and repeatedly, exactly the even coverage that could confirm or dissolve the clustering pattern, and exactly the sustained watch that could catch a planet drifting along its orbit. The best part is that this is no longer a promise. In the months before its formal survey began, Rubin ran a shorter trial phase, and even that brief warm-up produced results that show what the full decade will be capable of. To see why astronomers are so confident, look at what it found in just a few weeks. Before the 10-year survey officially began, Rubin spent several weeks in an early operational phase, tuning its systems and testing its performance on the real sky. That warm-up alone was enough to demonstrate the observatory's power, and the numbers it returned are the best argument for what it will do to the Planet 9 question. In roughly 6 weeks of that early observing, Rubin discovered more than 11,000 previously unknown asteroids. That is not 11,000 objects catalogued over years of patient work. It is 11,000 new worlds, small ones, found in a matter of weeks, in a trial run. Among them were tens of near-Earth objects, asteroids on orbits that bring them close to our own planet, the kind we most want to track. The sheer rate of discovery outpaced anything astronomy had seen before. Most important for our story, that early haul included several hundred trans-Neptunian objects, distant icy bodies orbiting beyond Neptune in the very region where the Planet 9 drama plays out. Finding hundreds of outer solar system objects in a brief trial phase is direct proof of exactly the capability the search needs. These are the faint, slow, distant bodies that are so hard to catch, and Rubin was pulling them out of the sky by the hundreds before its real work had even started. Think about what that means for the clustering debate. The whole Planet 9 case rests on the orbits of a few dozen very distant objects, a sample so small that a single misaligned world like Ammonite can shift the odds. Rubin is built to enlarge that sample dramatically, potentially finding many new distant objects out in the region that matters. A larger, uniformly discovered sample is exactly what is needed to settle whether the clustering is real signal or an artifact of biased searching. Rubin could turn a fragile handful of orbits into a robust population and let the pattern stand or fall on solid ground. And beyond enlarging the sample, there is the direct hope. If Planet 9 exists and shines in reflected light within Rubin's reach, the survey's repeated deep imaging of the whole southern sky gives it a real chance of catching the planet itself, as a faint dot that creeps from one image to the next. It would not need to know exactly where to look, the way a targeted search does. It looks everywhere, repeatedly, and lets a moving planet reveal itself by its motion against the fixed stars. The early results also correct a subtle problem in past catalogues. Because Rubin surveys so uniformly, its data can be used to measure and remove the observational biases that plagued earlier searches, mapping precisely what the survey could and could not have seen. That is the antidote to the deepest skeptical worry. A clustering pattern that persists in Rubin's even bias-corrected data would be very hard to explain away. So the trial phase was not just a technical success. It was a preview of a coming flood of our outer solar system discoveries, and a demonstration that the tool now trained on the Planet 9 question is up to the task. The observatory that could confirm the planet, refute it, or reshape the whole debate has proven it can find the faint distant worlds at the centre of it. What remains is time, and the patient accumulation of data across the survey's first years, and on that timeline, the people closest to the hypothesis have made a striking promise. The scientists who built the Planet 9 hypothesis are not asking for endless patience. They are saying, remarkably, that the answer is close, and that the next couple of years should decide it one way or the other. Konstantin Batygin has been the most direct about this. He describes the Planet 9 hypothesis as readily refutable, and he means that as a compliment to it, not a criticism. A good scientific idea, in his view, is one that sticks its neck out, that makes a clear prediction which new data can confirm or destroy. Planet 9 does exactly that. It predicts a real, findable planet in a real, definable region of sky. With Rubin now surveying that sky, Batygin expects that we will know, fairly soon, whether the planet is really out there or not. He points to this stretch of time, beginning in the summer of 2026, as a turning point. As Rubin collects data over its first months and years, he argues, it will provide a direct test of all the lines of evidence gathered for Planet 9 over the past decade. If Rubin detects an object at hundreds of astronomical units from the Sun, on an orbit matching the predicted range that Batygin says would essentially be the answer. At that distance, anything Rubin could see would have to be large, so a clear detection would be decisive. The ghost would become a planet. Other astronomers close to the survey share a version of this optimism. Megan Schwamb, a planetary scientist who works on Rubin's solar system science, has indicated that if Planet 9 sits within the main predicted search region, it will likely be found within the first year or two of full operations. The years of ruling out patches of sky have narrowed the hiding space enormously to a small fraction of what it once was, which means Rubin does not have to search blindly. It can concentrate on the corner where the planet must be, if it exists at all. That is a genuinely thrilling position for a long-standing mystery to be in. For most deep questions in astronomy, the honest answer to when will we know is decades, or never. Planet 9 is different. It is a rare case where a specific testable claim meets a specific powerful new instrument on a short and definite timeline. The people who proposed the planet are willing to say, out loud, that within a year or two of Rubin's survey we should have a real answer. Few hypotheses are brave enough, or lucky enough, to be settled so soon. There is a discipline in Batygin's framing that is worth admiring. He does not insist the planet is there. He insists the question is answerable. Whenever you find an interesting pattern in data, he has noted, the first thing to ask is whether it will hold up to fresh, unbiased scrutiny. Rubin is precisely that fresh, unbiased scrutiny. If the planet is real, Rubin should find it. If the pattern was a mirage, Rubin's even coverage should reveal that too. Either way, the waiting is nearly over. But there is one more thing to hold on to before we imagine the discovery, and it is the possibility that gets the least attention and deserves real respect. Rubin might look carefully and thoroughly and find nothing, and in this particular search, nothing is not a disappointment. Nothing is an answer in its own right. It is worth pausing on the outcome nobody puts in a headline. Rubin surveys the sky for its first years, combs the narrowed hiding space with its deep repeated imaging, and does not find Planet 9. No large distant world creeps across its images. The predicted planet simply is not there to be seen. What then? Michael Brown, of all people, has embraced this possibility with grace. Even a clean non-detection, he has said, would be an important result, another nail in the coffin of a planetary theory. Coming from one of the two people who proposed the planet, that is a striking thing to say. It reflects how science is supposed to work. You do not marry your hypothesis, you test it, and if the test comes back negative, you accept the answer and learn from it. A non-detection would not be empty. If Rubin's thorough, unbiased survey rules out a planet across the whole predicted region, that tells us something real about our solar system, that there is no large, reflective world in that zone, and that whatever shapes the distant orbits, if anything does, is not the planet we imagined. That would push the community toward the other explanations. Perhaps the clustering really was an artifact of biased observation, as the skeptics argued, and Rubin's even coverage would help show that by finding a distribution of distant objects with no real alignment at all. Perhaps the pattern is real but caused by something else, a broad disk of debris, or the fossil of a planet long since ejected, leaving orbits no telescope can find because there is nothing there now to find. There is a subtle point in how Brown frames the value of even a partial result. Rubin might not see the planet directly, and yet still discover many more distant objects with warped clustered orbits. If it does, that strengthens the case that something massive is shaping them, even if the something stays hidden. So Rubin can move the question forward whether or not it catches the planet itself. More aligned objects argue for a shepherd. A clean, unaligned distribution argues against one. A direct sighting settles everything. All three outcomes teach us something we do not currently know. This is the quiet maturity of the whole enterprise, and it is worth carrying out of the noise of the headlines. The word panic in the title of this journey belongs to a certain style of storytelling, the kind that needs every discovery to be a crisis. The reality is calmer and, in its way, more impressive. Careful people built a testable idea, spent a decade gathering circumstantial evidence, endured real and reasonable doubt, found a tantalizing and confusing candidate, and then built the instrument that can finally give a verdict. They are prepared, out loud, to be told they were wrong. That readiness is not weakness. It is the source of the whole thing's strength. A claim that can be refuted, made by people willing to see it refuted, tested by a machine designed to be fair, is science in its healthiest form. Whatever Rubin finds, whether a planet, a crowd of telltale orbits, or a clean and honest nothing, the answer will be earned. And this is not the first time our species has stood at exactly this edge, staring at unexplained motions in the sky and wondering whether a hidden world lies behind them. The history of that question holds both a triumph and a warning, and both are worth remembering as we wait. We have been here before, and history offers two very different endings to keep in mind. The story of predicting a planet from the motion of other things has one glorious success and several embarrassing failures, and Planet 9 could still become either. The glorious success is Neptune. In the 1840s, astronomers noticed that Uranus was not moving quite as the laws of gravity said it should. Its orbit had small deviations, as if something unseen were tugging it. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, working separately, used those deviations to calculate where a hidden planet must be to cause them. In 1846, astronomers at a Berlin observatory pointed their telescope at the spot Le Verrier had predicted, and there, almost exactly where the mathematics said it should be, was Neptune. A planet found first with pencil and paper, then confirmed with glass. It remains one of the greatest triumphs of theoretical science, and it is the direct ancestor of the Planet 9 search. The method is the same. Read a hidden world from its gravitational effect on the things you can see, but the same method has misfired badly. After Neptune, astronomers noticed small oddities in Mercury's orbit and confidently predicted another hidden planet, this one inside Mercury's orbit, close to the Sun. They even named it Vulcan. People reported seeing it. Expeditions searched for it. It did not exist. The oddities in Mercury's motion were not caused by a planet at all, but by the fact that Newton's gravity was itself slightly incomplete. Only Einstein's theory of gravity decades later explained Mercury's orbit correctly, with no extra planet required. Vulcan was a ghost born of trusting a pattern too much. Then there is Planet X, the direct namesake of this whole effort. In the early 20th century, Percival Lowell became convinced that unexplained wobbles in the outer planets pointed to another large world beyond Neptune, which he called Planet X. He searched for it for years. The search outlived him, and in 1930 at Lowell's Observatory, a young astronomer named Clyde Tombaugh finally found a distant moving speck. It was hailed as Planet X and named Pluto. But there was a twist. Pluto turned out to be far too small to cause the wobbles Lowell had chased, and those wobbles, it later emerged, were not real at all, just errors in the measured masses of the outer planets. Pluto was a real and wonderful discovery, but it was not the thing that had been predicted. The prediction was based on nothing. That history is why the field is so careful now, and why the caution around today's candidate is not timidity but wisdom. Neptune shows that reading a planet from gravity can work brilliantly. Vulcan shows that a confident prediction can point at empty space when the underlying theory is flawed. Pluto shows that you can even find a real object at the predicted spot and still be wrong about what it is and why it is there. All three lessons apply directly to Planet 9. It could be Neptune, a genuine world read correctly from the motions of others. It could be Vulcan, a mirage created by a pattern we misunderstand. It could even be a Pluto, where we find something real that turns out not to be the thing we sought, which is uncomfortably close to what the steeply tilted infrared candidate might already be hinting. Which ending we get, we do not yet know. But suppose for a moment the best one comes true. Suppose Rubin catches it, and the 9th planet is real. What would that actually change? Imagine the morning the announcement comes. A faint object, hundreds of astronomical units out, has been tracked across enough of the sky to fix its orbit beyond doubt. It is large, several times the mass of the Earth, cold and dark and slow, and it has been circling the Sun the entire time, unseen, for as long as there has been an Earth to circle beside. Our solar system would have a 9th planet, and every diagram in every classroom would quietly need to be redrawn. The change would be more than a new dot on a map. It would rearrange how we think about our own place in space. For all of history, we have known our planetary family as a compact thing, ending at Neptune, with a scattering of small icy bodies beyond. A confirmed Planet 9 would stretch that family outward by a factor of 10 or 20, revealing that the Sun holds a major world at a distance we had thought held only debris. The solar system would suddenly be much larger and much stranger than the tidy version we learned. It would also fill a curious gap in our cosmic self-knowledge. We have discovered thousands of planets around other stars, and the single most common kind is the super-Earth or mini-Neptune, worlds between the size of Earth and Neptune. Yet our own system, oddly, has none, or so we thought. If Planet 9 is real and falls in that mass range, it would mean the galaxy's most ordinary type of planet was hiding in our own household all along. We would go from being an exception, a system missing the common planet, to being ordinary after all, with our super-Earth simply parked far out in the dark. Then there is the question of where it came from, and here a confirmed planet would open a rich mystery rather than close one. Its orbit would carry clues to its history. If it lies on a moderately tilted, stretched orbit, that would fit the idea of a world born among the giant planets and flung outward early on, nearly ejected but not quite, marooned in the deep. If it lies on a stranger orbit, steeply tilted or backward like the infrared candidate's estimate, that would demand a more dramatic story, perhaps a world captured from another passing star during the Sun's crowded infancy, when it was born in a cluster of sibling stars close enough to trade planets. Either way, the planet would be a frozen record of the solar system's violent youth, a witness to events we can otherwise only model. And a confirmed planet would settle the decade-long argument in the most satisfying way, by vindicating a prediction. It would mean that Trujillo and Shepard's small clue about clustered orbits, and Batygin and Brown's bold reading of it, had led us truly, that a pattern in a few dozen faint icy worlds had pointed the way to a hidden giant, just as Uranus's wobble once pointed to Neptune. It would be a triumph of exactly the kind of patient circumstantial reasoning that the skeptics rightly stress-tested at every step. Of course, all of this rests on the word suppose. The planet may not be there, the candidate may dissolve, the clustering may fade under Rubin's fair gaze. We do not get to choose the ending, only to look honestly and accept what the sky shows us. But the possibility, held plainly, is extraordinary. There may be one more world out there, bound to our sun, waiting at the edge of the dark to be seen for the first time. So we come back to where we began, to the handful of icy worlds far past Neptune, tracing their long, slow loops, leaning and pointing in nearly the same direction, as if combed into line by a hand we cannot see. That pattern is still there, still unexplained in any settled way, still holding its quiet question open. Everything in this long journey has been an attempt to read it. We have followed the clue from its first noticing, through the bold idea it inspired, out past the difficulties of seeing anything so far and so dark. We have met the honest doubt that the pattern might be a trick of where we looked, and the rival suspects that might tug the orbits instead of a planet, a small black hole, a broad disk, the fossil pull of a world already gone. We have watched a clever search pull a single faint candidate out of decades-old infrared maps, and then watched the man who predicted Planet 9 look at that candidate and conclude it is probably not his planet, and might even rule his planet out. We have seen a new distant object refuse to fall into line, and a great new telescope open its eye on the exact question, promising an answer within a few short years. What we have not done is resolve it, and that is honest. The truth tonight is that we do not know whether Planet 9 is out there. We have a pattern that begs for a cause, a candidate that may be a planet or a mirage or something stranger than either, and a tool finally capable of telling us which. The panic of the title was never the right feeling. The right feeling is closer to patience, the steady attention of people who have built a question carefully enough that reality can now answer it. There is something worth sitting with in that, as the night settles. For all our maps and instruments, our own solar system still holds a genuine unknown, close enough to be part of us, far enough to have stayed hidden through all of human history. Whatever the answer turns out to be, the very fact that the question is open and answerable is a kind of gift. It means the age of finding new worlds in our own backyard is not over. Picture it out there, if it exists right now as you listen. A dark world several times the size of the Earth, moving so slowly that in your entire lifetime it will drift only a small way along its orbit. The sun, from its sky, is just the brightest star, giving no warmth. It has been circling out there in the cold and the quiet the whole time, through every year of every life that has ever been lived on Earth, unseen and unbothered, keeping its distant company of icy worlds loosely in line. Maybe it is there, maybe it never was, and we have been reading the shape of an absence. Either way, the sky above you tonight holds one honest, open question, waiting at the edge of the dark, and soon, perhaps sooner than for any great mystery before it, we will simply look and see.